I am not going to talk about the history of the internet. I'm going to talk about a history of the internet. Even people that were there together have disagreements on what happened. So I'm not going to talk about the history of the internet. So let's see here. Green button, okay. So this is a general overview. It's what I saw myself with my own biases and what I've researched and found. It's represented. It's certainly not comprehensive. There's a lot of people that are not included in this, this list. But I think it's a good way to understand how we got here. We started with Sputnik. So the Russians put up Sputnik and the US went bananas. If you were around at the time, looking around, I think that not everybody was around at the time. But if you were around at the time, it was a very big deal. Somehow we were at the pinnacle of technology and the Russians took it away. And that was a big deal. Lyndon Johnson said the sky seemed alien. Well, that was Lyndon. But in response to that, we had a president at the time, Dwight David Eisenhower, who believed in science. Now, some of you may recognize that that's not always the case with presidents, but Eisenhower believed in science, and he believed in appointing good people and listening to them. Well, he appointed Jim Killen as the science advisor, and he and Killen together put together the Advanced Research Projects Agency, the Department of Defense, in 3 months, which is a breathtaking speed for Washington. But in 3 months, they did that. Now, the clock says I have 43 minutes and 15 seconds. Okay. So the ARPA mission, the official mission, was responsible for detection and direction and performance of advanced projects, et cetera, et cetera. Unofficially, we find it in some of the documents, and the document pointers are on the slides. Unofficially, it was prevent another Sputnik. We don't want to be surprised by this. A name that actually is probably the most important name in the early whole concept of networking is Licklider. Licklider was at MIT. He wrote a number of very important articles. He then later on went to ARPA and created the ARPA Information Processing Techniques Office, which we'll come back to a number of times. But it was his general vision that computers could talk to each other over communication links was the basic concept. And this was very early on. This was in the early 60s. At a time when nobody really thought about that. All that was going on in networks those days was telephone calls. And that was me calling you, and the circuits were dedicated to my communication to you at the time. And Licklider thought that that was probably not necessarily the future. At about approximately the same time, a fellow named Paul Barron, who was working at MITRE and at RAND and Hughes Aircraft, sponsored by the Air Force, not sponsored by DARPA, sponsored by the Air Force. And he wrote in 1960, reliable digital communication systems using unreliable network nodes. The first idea of building a reliable system using unreliable components by introducing parallelism. This was a radical concept at the time, because this was the telephone world at the time was all 5 nines. The individual boxes had to be unbelievably reliable. And Barron said, no, you don't need to do that. If you have parallelism, then if a link goes down or a box goes down, you just go around it. He expanded that in 1962 to undistributed communication networks, which is the basic concepts of packet switch networking. Now, he didn't call it packet switch, he called it message switch, but it was still packet switch networking. It was packets with source and destination addresses, quality of service. So I don't know, he actually didn't implement any of this, and I'll talk about that in a second. And a payload. He said that the network would be a lot of switching nodes, which is routers, and store and forward, so the messages would go hop by hop between the boxes. Redundant pathways, and the picture there shows one of the pictures from his 1964 article showing the redundant pathways, and a routing protocol. All of this was pretty early on to do this sort of thing. He said that message block systems were better because you could mix together different communications running at different rates, which was a completely alien concept to the telephone world. The telephone world was all circuits and everything on that circuit was running at the same speed, which was your voice. And the idea that you could put multiple services on the same circuit just didn't make any sense. Circuit transfers take up a lot of time to do. Set up the circuits takes a lot of time, and with packet-based networks, you don't need to do that. Minimal retransmission after failover, go to a new route, you don't have to redo the entire message. Resilience in the face of failure. That picture there, the chart there, is a chart from his paper showing the probability of a message getting through compared to the probability of nodes being destroyed in an atomic attack. The idea that he needed a chart like that is kind of scary. Maybe it's coming back these days, considering what's the atomic clock looks like these days. But this was the 60s. This was when we were duck and covering and we were worrying about the Russians attacking us. And he wanted a system that would survive an attack. It was command and control system would survive an attack so that if the Russians attacked us, we could, with a first strike, we could attack back. But Barron's idea was slightly different. He wanted to do that, but he wanted to provide that same technology to the Russians so that our military would not consider that they could do a first strike and survive. And this was almost treasonous, but he felt that it was important to make it so that neither side could feel that they could have a first strike. All of his material was public. There were 2 documents that weren't, but everything else was public. He publicized it, went around giving talks, including one to AT&T. One of his original concepts was you could run voice over packet networks. That was in 1962. You could run voice over packet networks. He went to AT&T and explained it all to them, and he reports in one of the oral histories that AT&T said, "Son, let's explain to you how the voice works." So AT&T wasn't on board for this. He got offered that the Defense Communications Agency would build an instance of his network, and he turned it down because the Defense Communications Agency in those days was a complete telephone world. They had no concept of packets. They would have no concept of packets. They didn't believe it would work, and he felt that if they did build it, then it would be dead for a generation. So he turned down the offer to get it built. Meanwhile, parallel activities, Donald Davies over in England put together what he called a packet network, which was the same basic technology that Barron had come up with. He did his original work without knowing about Barron, later on found out about Barron, and basically he gave the name of packet networking to the whole concept. One of the people in his lab, a fellow named Scantlebury, presented a paper at a conference in 1967, and a fellow named Larry Roberts was in the audience. We'll come back to Larry, but Larry had been given the task of building a nationwide computer sharing network, and he knew he wanted to do it. He knew he didn't want circuits, but he didn't really know what exactly he did want. But at this conference, he was introduced to the concept of packet networking, and he seized on that. Bob Taylor had been taken over the ARPA IPO, so he was in charge of actually building a network. When he was given that, he was sort of given that responsibility, not directly, but very soon after he got there, or quite soon after he got there, he went and requested $1 million to build a nationwide computer sharing network. And his boss at the time, is reported to have said, because he approved the money in a half an hour or something, and the boss at the time said, "Oh, I was expecting you to come months ago, so I was all set to say yes, and when you came, I said yes, so you were a little laggard." But he built it. He wound up building the Arpanet. Now, the Arpanet was not a command and control network. The Arpanet's mission, and this is direct quotes from it, was to share computers, share resources. The computers in those days were big and clumsy and extremely expensive. Even the US military could not afford to give a computer ever to a research organization like Harvard and MIT and BU and et cetera. They couldn't give a computer to every place, so they needed to share them. And this was the Lichtliner's original dream, and it was also Robert's dream to build a network that would share these expensive resources. So it wasn't the bomb, even though it was the bomb's technology. It was Barron's technology, but the money came from sharing computers. And Larry Roberts was, I mentioned him already, he was the one who actually did the design and implementation. Taylor drove it, but Roberts was the one who actually built it. And he built it, he decided to use packet switch networking, and offline loaded the processing into separate boxes, now called routers, based on an idea from a physicist named Wesley Clark. This was a new concept, because the original concept was that the computers being interconnected was the ones that were going to be doing the processing. But they weren't designed for that. They were designed to do processing, big computer processing, big data tables and things like that. So Roberts decided to use these offline boxes, and the boxes would pre-process the data, and they would be the ones that would be forwarding the traffic and only connecting to an individual computer. Len Kleinrock's name comes up a lot. His PhD thesis at MIT did talk about queuing theory, about message queuing theory. He has been stated as the inventor of packet switch networking. There's dispute over that. He certainly was very important in the concepts, but he didn't lay out a whole picture such as Barron did, for example, or Davies did. One of the names that's an important name in history there, not of the networking itself, but of what to do with the networking, is Doug Engelbart. He was Stanford Research, and he put on in 1968 the mother of all demos, which included mice and real-time windows and real-time editing and everything that you now consider a computer to be. It came from Engelbart's 1968 demo. It's an amazing piece of work. There's a YouTube video of it. The link to it is on the slide. I urge you to take a look at it. You will see that this guy was more than a little bit ahead of his time. There's very little that we've got on all the ubiquitous computers and laptops in front of us that didn't come out of that demo. It's pretty amazing stuff. So in 1968, an RFQ went out for the little router boxes, then called IMPs, and it was interesting. They sent out a request for quotes to 140 companies and asked them to submit a bid. Only 12 did. The rest considered this stuff useless. Neither IBM nor AT&T bid on it. Both of them considered best effort packet networking to be something of no value whatsoever. BB&N put in a bid and they won it. And they installed the first IMP in September '69, which was pretty good. They got the first unit out there pretty quickly. There was some gestation pains, but it did work. This is the obligatory 4-node Arpanet beginning picture that shows up all over the place. The Arpanet expanded to the East Coast. A friend of mine from MIT reviewed these slides, and he said, "I must say that MIT got on before Harvard," so I put it on the slide. But expanded rapidly. But by 1980, there were only 200 hosts, which at the time seemed to be a massive number. But now is what you get in your bedroom, I mean, with the Internet of Things. So it's a very different world. But it was worldwide, well, not worldwide, but it was transcontinental and transatlantic. And it showed that this packet stuff could actually work. Well, not necessarily all that fast, because the backbone was 56 kilobits, which is kind of slow in these days, but it showed that this concept could work. You could actually share these resources. Bob Kahn comes in at this point. He moved to BB&N and worked on the IMP, and then moved to ARPA, and was part of the ARPA project's management. He realized that the then current design for the Arpanet was not ideal because it connected a computer in one location to a computer in another location. And really what you wanted to do was connect a network of computers to other networks of computers. And he asked Vint Cerf to help to create such a protocol to deal with that. And so the original NCP protocol was one which talked between those IMPs in a reliable fashion, and then would connect from that IMP. The IMP would be a connection from that IMP to a particular host, and communication that way. So it wouldn't scale very fast. You'd basically have to have an interface on each of the IMPs for each of the hosts, and that just didn't scale very well. Also, this provided reliable communications over the network. This was in an era of X25 and other kinds of telephone protocols which assumed the network itself had to be reliable. Not everybody agreed with that. Danny Cohen in particular, a speech researcher, had been working on speech over networks for quite a while, and he looked at the Arpanet and said, well, I really want to use that because it goes to where I want to use it, but if it only does reliable communication, then the quality of the speech will be crap. Because the only way you do reliable communication is you wait for figure out that the packet was lost, and then you retransmit that packet. And AT&T research, done and Bell Labs for a number of years before, showed that if there's a delay of more than 300 milliseconds in a round trip between me talking and then listening for you to start talking, then people talk over each other. Of course, that research was done with North American white males, so we don't really know what the average person is, but that was what AT&T was using as a subject pool. So he argued that, Danny Cohen argued that you needed an unreliable path, something that didn't correct for you. And there was they figured out how to use a bypass in NCP in order to do voice over the net in the early 1970s. They made a video in 1978. It's a very hokey video, and Danny Cohen's voice has been dubbed. If anybody knows, anybody here ever met Danny Cohen? So you know why you know why they dubbed the voice. He was not terribly understandable, but it's a very cute video. It shows him going misty-eye over sailboats, things like that. But take a look at it. But it'll come back here too. It'll come back in a bit. So Kahn realized you needed to be able to connect networks together and asked Vint Cerf for help. As I already said that. There was a proof of concept of such a network in France, the Cascades network, from Louis Poussin. And Poussin had come up with this network to connect together computers. And what he said in one of his oral histories was that his network ran over France Telecom. So he could not depend on network being reliable. It was a one-to-one relationship. No, France Telecom means not reliable. So he had to have multiple pathways and things like that. And he said that you couldn't depend on the network even delivering packets. They would do it out of order and drop them and all that kind of stuff. So he decided that the end nodes had to be responsible for the reliability of the communication, the end-to-end concept. The protocol that Cerf came up with, Cerf and Kahn came up with, initially IP-TCP, which was a protocol which was a reliable communications protocol that was then later on split into TCP and IP as separate, among others by Danny Cohen, who confronted Vint in a hallway in Monterey. I think it was Monterey. Him and David Reed and a couple of other people convinced Vint that there needed to be an unreliable path. And that's what UDP is. It's the unreliable path to let the end nodes decide entirely what the level of reliability wants to be. TCP assumed a particular set of code and functionality in the end nodes, and all TCPs needed to work approximately the same. UDP didn't need that. And so we've now, starting in the 1980s, early 1980s, we have TCP/IP with UDP as an unreliable path. And adding that unreliable path was an extremely important concept in the whole history of the internet. The end-to-end principle, which many of you have heard, and some of you may have actually read this article, the end-to-end arguments in system design by Salzer, Reed, and Clark from MIT, basically said putting functionality such as quality of service into a network by itself, or encryption or other kinds of security, and the network itself was a not good thing to do because there's no way for the network to know what the end nodes actually needed. Don't know what the right level of reliability needs to be or the level of security needs to be. And also, for security, if you're doing link-by-link security, then you have to trust the boxes in the network, and that's not as secure as going end-to-end. This principle has been overused in the internet these days to mean many more things than they meant. If you have the time, just read the article itself and you'll find it's not as complicated. So there's a they there. They is the people who weren't part of the internet, part of the Arpanet. This is not internet yet. Until TCP/IP was rolled out in 1983, this was the internet. January 1st, 1983, TCP/IP was rolled out on the Arpanet. That's the really beginning of the internet because it was network-to-network internetworking. The rest of the world was circuits. The regulators, the telecommunications companies, the big computer companies were all circuits. And they looked at this thing and they said, it's a toy. It's completely a toy. It's irrelevant. We don't care about it. By not caring about it meant the regulators didn't need to regulate it. And that turned out to be one of the most important pieces of the history of the internet, is the fact that people didn't consider it important enough to regulate. If it had been regulated, then particularly along the lines that telephone companies were regulated, every time you wanted to bring out a new application, you'd have to get FCC approval. I mean, you'd have to be involved with the regulators to do anything. And luckily, it didn't happen because they didn't think it was worth anything. So I have a bumblebee there. So why is there a bumblebee on the screen? Somebody should know that. Aerodynamic theoreticians proved that bumblebees couldn't fly. IBM said, quote, you cannot build a corporate network out of TCP/IP, and they said that in 1992. So by definition, you couldn't. I was a ribbon wearer at the Share user conference, which is an IBM user conference. How many here have ever been to a Share conference? Not one person here knows everything. Share was actually a very good user conference because you got IBM brought their developers there and you really had time to interact with them. But IBM was saying you couldn't do TCP/IP. I was a ribbon wearer, co-chair of the TCP/IP working group. At Share, you have little stickers you put on your badges to indicate what you're interested in. I said, okay, so we needed a sticker. The stickers were things like if you're into communications, it's an octopus because it goes everywhere. If you're into numerically intensive computing, it's a circle with a 42 in it. And if you didn't know what that meant, you didn't get one. We chose the bumblebee because IBM said it wouldn't fly. The bumblebee didn't give a crap, kept flying, and we kept flying. But that's the environment that we were in, that the regulators, the traditional telecommunications people said this wouldn't fly. And that was very, very important because it got the regulators off our backs. This Nethead versus Bellhead article is a very good one to explain it goes into the mindset at the time, which was pretty ugly. It was a pretty ugly mindset. This was ATM versus IP. Thing. And then the article at the bottom is The Rise of the Stupid Network by David Eisenberg. Eisenberg was an employee of AT&T until shortly after he wrote this article. The article basically says, it's the bits, stupid. Just deliver the bits. Get out of the way. Your job is not to add value, just deliver the damn bits. And he didn't last long at AT&T, and in fact, to this day, he cannot post a copy of this paper on his website. There are links to people who have posted copies, but AT&T says that he can't post a copy. Now, there's a deep thinker at AT&T there. So then we got some commercialization, stuff started moving along. One of the important pieces at the very beginning was NSF had said that on the NSF-sponsored and then ARPA had said on the ARPA-sponsored networks, you couldn't use them for commercial use. It got a little fuzzy there because you could use it in support of research. So I could send a note to my DEC salesman and ask what the price on some computer was because that was in support of research at Harvard. But commercial ISPs were formed because of the fact that Uncle Sam wasn't going to carry the commercial bits. The commercial networks started forming, PSINet and UUNet and the like. And some of Sprint's networks were that, and Internet MCI. If without that blockage of commercial traffic, you wouldn't have had the incentive to create the commercial networks. So that was pretty important. Commercial Internet Exchange formed, and then some additional use of the NSF for commercial use, but still not enough to be completely open. May East, May West, the NSF net closed. So we now have a fully non-US government-sponsored network, internet, by mid-1990s. And then the web happened. A few years ago, I was asked, what was my biggest surprise coming from the 70s and 80s, looking at the internet of today? My answer was mom surfing. It never occurred to me that my mother would use this magic. Because in the old days, it was you type magic incantations and magic happened. But you needed to know the magic incantations. And the web came along and said, you don't need to know any magic incantations. All you need to be able to click. So that changed the world. It changed not the underlying technology. The underlying technologies have been remarkably similar the entire time. From the time that TCP/IP was first deployed until today, there have been some tweaks, but fundamentally, the protocol's the same. Going from a 56 kilobit network to hundreds of megabits networks, it's the same protocol. Those guys did a pretty good job. They actually know what they were talking about. But now the web exploded. They were up to 1 billion nodes in 2015. It was kind of a big deal. Little hard to now ignore it. The regulators started to realize this was not just a toy anymore. So this is a set of different decisions that I think made the network of today. Some of these came from research papers. The first one is from Dave Clark's talk about the paper about the origins of the internet protocol. The decision was to support existing networks, not to build a new network. Don't lay new fiber or new wires. Use what's there. The original Arpanet and the successor internet ran over the telephone network. The telephone network didn't know what was going on, but there was bits flying over it, and the layering on top was an important thing. Now, of course, the layering on top is HTTP over the network in order to get rid of some of the control we have. Datagram-based rather than circuit-based. The router function to interconnect networks, split TCP and IP, in order to support non-reliable functions, like voice, like streaming video and streaming audio. All of those are much better with UDP. A huge thing was that in those early days, there was a bazillion companies building little workstations. And most of them started out building their own network protocol. And there was dozens of network protocols out there for a while. But DARPA funded Berkeley to put BBN TCP into Unix. And now you could go and get a Unix a distribution from Berkeley of Unix. You had to pay your AT&T license fee of a few $100. And you get a tape that had a full TCP/IP distribution on it. It was now much cheaper to use TCP/IP than it was to invent your own protocol. It would take a lot of programming effort to do your own protocol, and you just plug in the TCP/IP. So we moved from an environment where there was incentive to build your own playing field to one where the incentive was reversed. The incentive was to use a consistent protocol. The United States Postal Service at one point looked into electronic mail and decided it wasn't mail under the definition of the Postal Service. If they had decided the other way, it could have gotten really sticky, because they, of course, have to control and charge for mail under their mandate. But they decided it wasn't really mail. At Harvard, when I first started, got my first Arpanet account in 1971, probably. 71 or maybe 72. But from then up until 1983, I couldn't let random people onto the network. It was prohibited to use, the Arpanet use was prohibited for anybody who didn't have direct federal funding. So all of those students, all of those faculty, all those staff at Harvard couldn't use it. It was there and they couldn't use it. The first general networking that many of them did was BitNet. It wasn't the Arpanet. It wasn't email on the Arpanet. But in 1983, CSNet, which was then recently formed, did a deal with the Arpanet to make it so that if one got their CSNet connectivity via Arpanet, then you could open up the Arpanet for email to anybody. So in early 1983, we were able to take down all of the blockage, and every student, every staff member, and every faculty member at Harvard could use the net. That meant that we created generations of students who knew this stuff, who knew how the power of email, the power of this type of communication, network communication. And they would, once graduated, they'd go out to the business world and come into the company and say, what do you mean we can't run email? You got to get on this thing. You got to go off and get on to PSINet or something. You need to, so they forced the companies that were hiring them to join this internet thing at a time when most companies didn't see any value in it. And a lot of them really objected to it. I started writing a column for Network World in the end of 1992. And for the first 9 or so years, I'd write about the internet every now and then, every 4 or 5 articles. And I got pushback from Network World that was too much. Businesses didn't care about this internet thing. They wanted Apple Talk and XNS and things like that, Novell networking. It took almost a decade for them to come around and say, well, maybe this internet thing is real. And that came from the fact that all of those students were now out there in the business world. NSF required TCP/IP on NSFnet, so you couldn't use Apple Talk or DECnet on the NSF net, which forced companies to support TCP/IP, particularly DEC, Digital Equipment Company, which did support it in various places, but it wasn't a upfront supporter until this sort of thing happened. We had a VMS machine at Harvard talking to a VMS machine at the Princeton Supercomputer Center, and they had to communicate over TCP/IP because it was over the NSFnet sponsored link. And that meant that DEC had to support the gateways both directions, and they did, but they weren't happy about it. We went through a formal process of getting turned down, which was exactly what I wanted. I wanted the NSF to turn us down in the request to support DECnet. And they did. Another piece was that early on, Vint Cerf and then the then chair of the IAB, Lyman Chapin, recognized that the Europeans were working on, the OSI folks in Europe, were working on a data communication standard for the future. And they offered TCP/IP. They said, you could take over TCP/IP and you can be the standards maintainer for that. Now, if that had happened, we would have had the ITU being the manager of TCP/IP, the ITU, who is responsive to governments, whose main membership is telephone companies, would be designing protocols that were designed to prolong the life of telephone companies. This was probably not what we wanted, and luckily, they turned it down. They turned it down most likely because they were afraid that if they accepted TCP/IP as the basis of the new protocol, then the US companies would have a big step up on the European companies. And so the US would come in with all of this stuff and the Europeans would be paying catch up. So they invented an entirely new protocol, the OSI protocol suite. And everybody was equally dissatisfied with that, as Margaret Thatcher has once reported to us said about consensus. It's not when everybody's satisfied, it's when everybody's equally dissatisfied. Well, that's what we lucked out on that one. They said no. The NSF appropriate use policy, blocking commercial use, and minimal regulation. The fact that the regulators thought this was a toy until too late was a big win. So today's internet, we've got a number of big issues going on, network neutrality being the most obvious one of them. It's attempted to get regulation, to get governance. A lot of countries think that governance is vital. The former president of France said it's a moral imperative to govern the internet. A moral imperative, coming from a Frenchman. Well, okay. But it didn't happen. We don't have governance. We don't have governance today. We really don't have anything. The network neutrality stuff, what it was passed by the previous version of the FCC in the US, was not really governance, because it was said, here are the 4 things that we're going to enforce, which is openness. That the network can't block any legal communication, it can't block any access to legal sites, it can't block access by any legal device. Leaving what legal meant up in the air, but that was the principles. And that wasn't really governance, because it was saying, let go. But it was approximating governance. Now what we have now is that the ISPs are legally enabled to screw their customers. That's all they have to do is tell you they're going to do it. It's a different approach, but that's the approach we have today. But it's a very widespread feeling amongst governments, particularly governments like France, like Russia or China or India, that they want the real governance to be part of the future of the internet. Well, it hasn't happened yet. I'm completely shocked that it hasn't. The last decade, I've been expecting real governance to come out, the ITU taking over things or being handed things to the UN. The ITU can vote itself in as the governor, because it's countries doing the voting, but it hasn't happened yet. So ever since the early 80s, mid-80s, there's been this thing which said, well, the internet isn't the future. This internet is just this toy. There's something wrong with it. It's just a toy. If you haven't seen it, that's the little picture there is from a movie called A Touch of Evil. How many here have seen that movie? So a few more people, not many. Culturally deprived folks here. So A Touch of Evil is Orson Welles' story of a corrupt sheriff in a border town, Mexican border town, or US border town with Mexico. And there's a scene in there where Orson Welles, who was padded, this is before you put on the real weight, he was padded, comes into Marlene Dietrich, who is a brothel owner, and asks for her to read his future. And she says, you haven't any. He said, what do you mean? Your future is all used up. Well, that's quite a line. He gets shot quite quickly after that. So that's been the feature about the internet is all the time people saying its future is all used up. First of all, it was ATM. We're going to replace everything. All with ATM, end-to-end. ATM is going to be the new network, going to replace all TCP/IP and everything else. And then MPLS was going to be this, as Randy Bush once put it, the local gravity well of MPLS, take over the world. And the ITU thought that too, because they did a next generation internet, the next generation network, NGN, which relied on basically MPLS to the desktop. But here's things that they want to go back to this circuit kind of stuff. They don't believe in the packet things. And then there's things like the cellular stuff. I ran into somebody, one of the folks from the cellular world in Taiwan at a meeting, and he was completely baffled as to why people were still building their own campus Ethernets. This was because 3G would take care of all of it. There was no reason to build your own network. And the same arguments of 4G and 5G, and it will be all the telephone company doing it to you, or for you, depending on your point of view. Information-centric networking, all intelligent networking, all of these things are things that which are going to theoretically succeed the internet. Luckily, none of them have. So, the controlled internet is one that a lot of people want. Newt Gingrich here once said that it's the role of government to guide technology. Well, a guided and controlled internet would not be the internet you and I know. In 1996, I said there was, at a Harvard meeting, or actually a meeting at the Federal Reserve, that there was 2 questions that were unanswered about the internet. Who says who makes the rules? The rules themselves are local, because if technology makes one set of rules, interconnections another set of rules, and different people make those. But who says who makes the rules? We have no way, we have no mechanism to say who makes the rules, and who pays for what. We still don't, those questions aren't answered. Others have asked that same sort of question before and since. But so 20 years ago, I was a witness for the American Library Association in the Communications Decency Act hearings, where the ACLU and the American Library Association sued the government to block the implementation of the Communications Decency Act, which blocked your ability to send material that somebody under 18 and anywhere in the world shouldn't see. And I said in response to a question from one of the judges that the internet was chaotic, but the strength of the internet was that chaos. It was the forum to innovate. And the question we have today, and what I don't have an answer for, is will that forum continue? Thank you. So we have time for a question and a half or so. Any questions, comments? Well, it says on the slide, it says on the slide you're only supposed to ask questions. So, any questions? No, well, maybe not. So maybe so I guess I'm done. Thank you.